Thank you. I'd like to thank the organizer for giving me the opportunity to give this talk here. So what I'm going to talk about is modular representation theory and the problem of classifying blocks. Now, we already had an excellent introduction to block theory in the talks from Marcus. So I'm going to go quite fast on this part. So just a reminder, we have a finite group G, and we're interested on its representation theory with the group algebra on a field with characteristic P that divides the order of the group, in which case most groups have wild representation theory. And so we define this P modular system, which is made of an algebraically closed field of characteristic P, a field of characteristic 0, which is big enough, and O, which is a complete discrete evaluation ring that is kind of a bridge between the two. And we can form the group algebra, and there is a decomposition of this group algebra as a direct product of indecomposable objects, which are called blocks. A way to realize blocks is to decompose one into the sum of certain primitive or orthogonal, primitive central idempotents which are orthogonal. This is always possible because one is itself a central idempotent, and if we do this, we can get P blocks. We can associate to a P block a defect group, as we have seen. There are many ways to do this. One way is just to take a minimal P subgroup that contains a vertex of every indecomposable module lying in the block. But again, there are many different definitions that we've seen. And there is a conjecture, Donovan's conjecture, which says that if you fix a P group D, then you have only finitely many Morita equivalence classes of blocks with this defect group occurring among the class of all finite groups. And this is still open for many classes of groups, but it has been proved for a few cases. I'm not going to mention them all. I'm just going to mention the ones that are relevant in some way. So it's been proved when the P group we choose is cyclic, which is a good situation because the representation type of a group, of a block with cyclic defect group, of a group algebra of a block with cyclic P0 is finite, and we can kind of relate to that part. It's been proved for P equals 2 and the elementary abelian in 2013, and then for P equals 2 and any abelian defect group D in 2018. And many more cases. There are various point of views you can take with Donovan's conjecture. You can restrict the classes of groups you look at, or you can impose additional restrictions on the defect group, such as it being normal, for example, as we have seen in Marcus' talk, or other types of restrictions. But Donovan's conjecture has been proved, but once you know there's a finite number of Morita equivalence classes of blocks occurring, it is maybe interesting to know which ones occur, so to classify them all. And the proof, in general, does not produce this list. So in particular, it is interesting to look at what are these blocks, especially for relatively small P groups. And we focus on the elementary abelian case. It will be somewhat clear why in a bit. But so P equals 2, D is C2 to the n. We know from 2013 that Donovan's conjecture holds, and we want to see how many classes there are and what are these classes and what are the properties. So for n equals 1, so for C2, we just have one class, which is quite easy to see using Brouwer trees. For n equals 2, there are 3 classes. This was done by Hartman in '82 over the field K, and then by Craven, Eaton, Carson, and Lincoln in a paper from 2018. For n equals 3, there are 8 classes, which was done by Eaton in 2014. And for n equals 4, there are 16 classes, which was done by Eaton in 2017. Now, for n equals 5, which was the main problem of my PhD thesis, really, there are 34 classes. And if you think you're spotting a pattern, not really, because for n equals 6, the candidate list has 97 or possibly more Morita equivalence classes of blocks. So it grows faster than the order of the defect group. So what I want to talk about is actually how does one go to classify blocks? What kind of input data do I need to hope to be able to produce a list of these blocks? And this is the question I want to answer here in this elementary abelian case. Now, the first object you absolutely need with using this method is knowing what the blocks of quasi-simple groups are with a smaller defect group than the P group with a smaller or a subgroup, which can be improper, of the P group you're considering. And for example, like we said, we had this from the paper in 2013. The same one that proved Donovan's conjecture for elementary abelian also classified blocks of quasi-simple groups with an abelian defect group of order 2 to the n. And then what else? This is the question I want to answer. So I will describe what the method is and tell you what kind of things we need to know about the blocks with defect group D or other objects to be able to answer this question. Okay, so the most important relation we're going to use between blocks is the covering relation. Now, we haven't seen it in this workshop. It's quite easy to understand. When you have a normal subgroup of a group G, and you have a block of G and a block of N, then the one block over each other, if the product of the idempotency is non-zero. One modular way to think about this is that there is a module in the little b, in the block little b, whose induction has a summand lying in big B, or vice versa. So there's a module in big B whose restriction has a summand lying in little b. And these two notions are equivalent when N is normal, which is the only case we care about. And the important thing about this relation is whenever D is a defect group of B, then the intersection with N ends up being a defect group of little b. So this behaves really well with the question we're asking, because if we pick a block with defect group D and we look at normal subgroups of this group, we're only going to, and blocks covered by this block, we're only going to get smaller defect groups. And so the way we do this, the way we pick this smaller normal subgroup, is by looking at the generalized fitting subgroup, which is a very important tool, which is also used in the proof of declassification. And it's just the central product of two normal subgroups, which are the fitting subgroup, which is just the product of the P of the L cores for primes dividing the order of the group, and the layer, which is the central product of all components of G, which we've seen before as well, but they are just subnormal quasi-simple subgroups. And the most important property is that, well, other than being normal, it is self-centralizing. So in a way, it controls the structure of the whole group, because the quotient, so what's left, can be embedded in the auto-automorphism group. So what's the important thing about the generalized fitting subgroup is that we know, if we know the blocks of quasi-simple groups, then we, after suitable reductions, we know what blocks appear as blocks of the generalized fitting subgroup. And then it becomes a matter of looking at, using the relation of covering, looking at what kind of blocks can cover these blocks. Make that a little bit more specific. So we pick a block of OG with defect group D. We're working over rho, by the way. It will be clear why it's very important to be over rho, to use a certain method that I'll talk about later. And but so first, just don't think about it. It could be K until there's something that holds only over rho. So we take B, a block of OG with defect group D, and we apply certain standard reductions, and we can assume that B, all the blocks covered by B are stable under conjugation by G, and every odd P prime, so odd P core, is central actually, and B essentially covers no nilpotent blocks, as in all nilpotent blocks that are covered are in the fitting subgroup. And this is quite technical. It's not super important to understand it, but it might answer some questions which could come up after this. So we apply certain standard reductions, which are mainly Phong reductions, and we can reduce to a special kind of block in a special kind of group that has these properties. And now, using Schweiz's conjecture, there are several situations in which we can actually show that G mod f star of G is a solvable group. Now, this is not always true, so actually this is something we need to put in the input list. We need an argument to reduce to a solvable quotient, as far as this method goes right now. It's often possible to get it, either because the defect group is small and you cannot have too many components. Of course, the auto-automorphism group of quasi-simple groups will be solvable, so the problem could be in these auto-automorphism groups interacting with between each other, but for C2 to the 5, for example, it is possible to reduce to G mod f star of G solvable. But in general, I'm not aware of general arguments, so I'll put it in the input list in a way. So whenever this holds, what we do is that there is this chain of normal subgroups between G and f star of G with prime indices, which can be either 2 or not 2, so either even or odd, and these two cases end up being really different. And there's a corresponding chain of blocks that we can pick between little b, the block of f star of G covered by B, and big B. So we have this chain. So the problem reduces now to a question, which is an extension problem. If we have a normal subgroup with prime index, and we have a block that covers another of the normal subgroup, and we know the Morita equivalence class of the block downstairs, what can we say about the one of the block upstairs? Can we give a final list of possible Morita equivalence classes that can occur? This way, applying this argument inductively, we can build from f star of G, which is known, all the way up to G, and we're going to get the full list of blocks that can occur finite groups. So remark, like I said before, we can actually determine all the possibilities that can occur here. Here it's quite important for you to be elementary abelian, actually, not to deal with non-split central extension, because it's a central product and not a direct one, but that's quite technical. So we know all the blocks downstairs. So this is a good starting case, which entirely comes from determining the blocks of quasi-simple groups with defect group D. Now, in general, this is a hard question. So actually, the hardest part is probably this one in this whole process. So we need to know all blocks with defect group D or subgroups of D in quasi-simple groups. And for certain classes of groups, it might be not easy, but manageable. For other classes, it's probably hopeless right now. But if we assume we have that, how do we produce a list? So the first thing we examine is when we have an even extension. So the index of the normal subgroup is 2. And there is a theorem from Cauchy-Tanner and Sommer that tells you that if the defect group of D has such a decomposition, so if there is a complement to the intersection with the normal subgroup, then B is the simplest object it could be, so it's Morita equivalent to the tensor product between B and this complement. Now, in our example, Q will be C2. So we're going to have a normal subgroup N inside H of index 2. And what happens is that there's a block B here and a block big B here. And big B is Morita equivalent to just B tensor KT2 over K, of course. And this is also a block of N times C2. Blocks of a direct product are tensor products of the blocks of the factors. So this is ideally the best it can happen. It's the best block we could hoping to get. There's a slight problem here is that this result is stated over K, and the proof of this result only works over K. So to be able to use it over rho, which again is important for the method we use for odd extensions, we need something. We need something more. So there's a theorem for Watanabe from the year 2000 that tells you that if B admits a GB local system, which is a notion defined by Usami and Puig, then in the situation above, B will be Morita equivalent to B tensor OQ. So this Cauchy-Tanner Sommer will hold over O. Now, I thought I wouldn't tell you what a GB local system is, but actually, in his talk, Marcus defined B-Brouwer pairs, so I can give you a rough idea. So a GB local system is this object. We have a group G with a block B, and as we've seen, that's a Brouwer correspondence. So in NG of D, we're going to have a Brouwer correspondent. We're going to call it little b. This is, of course, not a normal subgroup. There's a Brouwer correspondent, which is the block corresponding to this, and we've seen that this defines also Morita equivalence class of the block. We know blocks with a normal defect group, and they were of this form, if you remember, where E was the P prime group in the automorphism group of D. And now, what is this GB local system? Well, you can take a list of Brouwer pairs, so you've got D, and in general, you've got a P subgroup Q inside D, and a Brouwer pair is I'm gonna write it like this, because it's the notation some input use. But in general, this would just be the block of CG of Q, which gives you a B Brouwer pair. And if you fix the block associated to the Brouwer correspondent, then you're going to have a unique choice for each one. If you remember, Marcus defined an ordering. And all a GB local system is a system of perfect isometries between the block of ECG of Q. OK, I won't tell you what a perfect isometry is. I'll tell you what an isometry is in a bit. Of ECG of Q and this, well, let's do it over K for simplicity. Pretend this is K. K alpha CL of Q. So and this is, of course, CG of Q, ECG of Q. So it's a system. There's a lot of perfect isometries, and they have to be compatible in some sense. And if you prove that a GB local system exists, then in particular, when you pick Q equals 1, you're going to get something between B and K alpha of D semidirect E. Oh, sorry, that's what I forgot. Call this L. You're going to get an isometry between these two objects, and really this is what you're after. But the way to produce this object is a bit inductive, so you need to actually get the whole GB local system in order to have this. And once you have this, you can give a proof. Now, what is an isometry? It's just a perfect isometry is a special kind of isometry between the generalized group characters of this. So you have the space generated by the irreducible characters of this, and the same thing here. And you want an isometry between the two, which has some other special condition attached to it. So the important thing, in a way, is that this is to prove something. There is a GB local system. It's a bit of an inductive process, but it's really a notion on G and B. Like, it's not something you automatically have because you know what's going on at the level of f star of G. It's something you need to know is already there before proceeding. So you need other methods. You need to have studied blocks with defect group D in another way before proceeding with classifying. So you need the existence of GB local systems, which is a condition on B and not on B. And before going to this, now it can be checked computationally, of course not in all cases, but there is the method of Usami and Puj can be implemented computationally. This has appeared in a recent paper by Benjamin Sambal and myself. The method doesn't work in all cases, so there might be that the computer method fails, but you can still apply Usami Puj to show there is a GB local system. And important global local conjectures predict that there is actually always a GB local systems. But the Usami Puj method to produce one might not work in those cases. So this can also be a hard question. And the second part is that this might seem like a theorem that is actually too nice. What do I mean? Well, every time we do an extension by C2, we're only going to get the nicest block we can have in a way. But really, what is hidden here is that this is true because D is elementary abelian, and you always have that kind of splitting. And what happens in real life is that most time you extend by a C2, you just get a bigger block with a different defect group. But you don't care about those because you're classifying blocks with defect group D, and so you discard those. So this is why this theorem looks too nice in a way. And so that is for even extensions. We're able to just add the times C2 to the block we have until we have exhausted the defect group, and then everything else will be odd. So what about odd extensions? What do we do? It's a bit more convoluted here, and because mainly the defect group is not giving all the restrictions that it was given before. So some definitions. What is a G-graded algebra? It's just an O algebra that admits a decomposition, which is compatible with group multiplication. And a cross product is a G-graded algebra such that every component contains at least a unit, so an invertible element. Main example, OG is a cross product of G over N and ON. And now, if you think about it, there's a block B of OG that covers a unique block of ON. So if you multiply left and right by B, the block B is actually a cross product of G over N and little b. So these two objects we're trying to relate are related by one is a cross product of the quotient with the other. And there's a theorem from Kuhlsammer 1995, which actually tells you how to classify these cross products between a ring R and a group X. There's a parametrization given by this homomorphism between X and the auto-automorphism group of the ring with a special condition on the 0,3 cocycle and some 2 cocycle. But like I said before, G over N will always be cyclic in our case, which is actually why we need the solvable thing, because we don't want this cohomology. So we can, that second cohomology group is always 0 in whatever case we're studying, so we can only look at omega. And what is the problem here? The problem here is that we're looking at Morita equivalence classes of blocks. So suppose that if we have two blocks here, B1 and B2, then we can, and two blocks B1 and B2 up here, then we can certainly, this is a cross product of these with some quotient, and this is also a cross product of these with some quotient for some groups N1 and N2. But nothing tells us a priori that these two objects are Morita equivalent or anything else. Like, it's not obvious that if these two are Morita equivalent, then these two are Morita equivalent. So we need to do something else. We need to pick some canonical representative of the Morita equivalence class, and this will be the basic algebra of the block. I've written is as FBF because it can be specified by multiplying left and right by a certain idempotent. And once we pick the basic algebra, okay, so they are Morita equivalent. And it was mentioned also in another talk, I don't remember which one. If you have two Morita equivalent blocks, then the basic algebra is isomorphic. So it's a good thing because now if you put a basic algebra here and here, these are isomorphic, so these will also be isomorphic if they are the same, if they're specified by the same parameterization as cross products. And in our setting, B and FBF, which is not always the basic algebra of big B, but it will be a cross product, are also Morita equivalent. So this is exactly what we were looking for. And we can parameterize equivalence classes, Morita equivalence classes for FBF, which is all the Morita equivalence classes of the block big B covering our little b, by studying homomorphism between G over N, which is parameterized by, well, it can be anything a priori, and OT FBF. So the problem becomes, how do we study OT FBF? How do we determine these automorphism groups of the basic algebra? And it can be done with, it has been done in the past with quivers and relations. So you express the basic algebra as a quiver, and you compute what automorphisms you could have, but it is hard. And a better thing to look at is the Picard group. Now, if you've never heard what the Picard group is, it's not actually super important, but the Picard group of a block is the group of bimodules that induce a self-Morita equivalence of the block. And what's important is that there's always an injective map between the automorphism groups of the block and the Picard group, and it is a Morita invariance, and in particular, this map is the identity, I think, between when the algebra is basic. And OK, the Picard group of a block of Kg is usually infinite, even from very small examples. So this would not be good, but the Picard group of a block of OG is always finite, as was shown by Florian Isale 5 months ago, I think. And so it is a good object we can compute and work on this and actually finally get a complete list for B. I also want to mention that the Picard group of a block is interesting in its own regard. Like, studying the Picard group of a block is an interesting problem independently of whether you're trying to classify blocks or not. So it is an interesting object there are many papers published and being published recently about Picard groups of blocks. And so we can compute, if we can compute Picard groups for all blocks, we can list our possibilities for B. And now just a quick example to tell you why, just to give you an idea why this is very necessary. So imagine we have defect group C2 cross C2. Can we all see here? Not really. Okay. Imagine you have defect group C2 cross C2, and you're looking at a block B, which is, well, imagine you're looking actually at N equals A4, which is itself a block. So your block B will be OA4. Now, the automorphism group of A4 is C2, but the Picard group of OA4, as computed by Boltje, Kessler, and Lincoln in 2017, is S3. So our theory predicts that there would be a block expressed by a C3, so that would be omega from a certain C3 to OT B. That is going to give us a group G associated to this omega, in which there is a block B, such that FBF is a cross product of OA4, which is its own basic algebra, and C3. But we don't know if this actually occurs. So we need to search for examples for everything that this theory predicts and produce an example to actually know this occurs in our list. And indeed, there is an example in quasi-simple groups, which, well, was known before this theory, so that was not too hard. And there's a block of PSL37, Morita equivalent to A4, and there's a block of PGL37, which is nilpotent that covers A4. But if you were just looking here, you couldn't see it because the group does not admit a C3 automorphism. So this way, you're really looking at the block, but you can compute the Picard group of a block also by looking at group theoretic invariance. So you're removing the problem of, I'm looking at a basic algebra and I completely forgot about group theory because the basic algebra is not necessarily related to the group that has the block it was produced from. So yeah, this is why this approach works better. And OK, yeah, OK, this is what I just said. So some might not occur as blocks of finite groups. So far, I haven't found an example. So I found an example of every single thing that was predicted. But eventually, I think classifying blocks with a certain defect group, that would be something that either does not occur and you can prove it, or would be a bit mysterious. So maybe it occurs, but we don't have a group in which this actually happens. So OK, to finish real quick, classify blocks with this defect group, we need classification of blocks of quasi-simple groups, a reduction to a solvable quotient. Ideally, there will be M will pretty much always be the generalized fitting subgroup after some reductions. Existence of GB local system on certain blocks. You don't need all of them a priori, because during the process, depending on groups you're looking at, you might take some shortcuts. And same for Picard groups. But you need to be able to ascertain the existence of GB local systems and compute Picard groups of blocks in order to produce this list. And for 2 to the 5, these were the 4 places in which this was found. So there was the paper from 2013 I mentioned before. Schweiz's conjecture and a theorem of Puig quickly proved that the quotient is solvable. Usami, Puig, Watanabe plus 2 new situations that I needed to compute. And then the Picard groups I needed were computed in these 2 papers. And last remark, what do they look like? What are these blocks? There's a wiki, which was also mentioned by Marcus earlier, maintained by Charles Eaton, and you can look at all the blocks you want. Like, I uploaded them all now. And so if you're curious, like, what do they look like? What properties do they have? You can just log in at the wiki. And of course, if you have more lists of blocks, you can also contribute. And yeah, that's all I wanted to say. I don't see why not, in principle. Yeah, there will be a list of representatives, so which will hopefully be the smallest example. So, I mean, in the list 2 to the 5, there's 34 blocks, so there will be 34 groups which have such a block. Like, they're not abstractly predicted. We actually have examples for each one of them, so I suppose then you can load them on your favorite algebra system and compute the center, well, yeah, maybe on a finite field or something, but I suppose yes. Like these are actual groups which have those blocks, so I suppose yes.